drift into a quieter corner of the universe where gravity shapes light and time with patient precision. Tonight's journey follows the missing middle, intermediate mass black holes. Too large to be ordinary remnants, too small to be galactic giants, yet powerful enough to leave subtle signatures in star clusters and faint stellar shells. If this kind of calm science storytelling helps you unwind, please tap like, subscribe for more long-form space documentaries, and turn on notifications so the next voyage arrives right on time. Now let the noise fade, let the scale expand, and let the quiet evidence guide the story. A quiet kind of absence can mark the place where a hidden mass shapes everything nearby. The missing link can be an intermediate mass black hole that bridges small remnants and galactic giants. In that region, darkness is not a colour. It is a boundary in behaviour. Light follows curves that feel gentle. Gravity still sets the rules with no visible surface. A dense cluster of stars drifts in slow formation. The centre looks ordinary at first. The outer stars keep wide spacing. Their paths look like calm loops. Closer in those loops tighten. The tightening is the first clue. Intermediate mass black hole, a black hole between stellar and supermassive. It sits in a middle range that feels strangely empty in many catalogues. It is like a missing weight in a balanced scale. One pan holds many small stones, the other pan holds a single boulder. The middle weight is the piece that would make the balance predictable. That missing piece matters because it can explain how the largest black holes begin. It can also explain how clusters evolve over long time. The first physical detail is simple and severe. There is an event horizon. It is a one-way boundary for light. Nothing solid marks it. No shell surrounds it. The boundary is defined by escape. A signal would fail to climb out once it crosses. The edge has no thickness that can be touched. Yet the idea has shape. It is a sphere in simple cases. It grows with mass. The sphere is not a wall. It is a limit in the possible paths of light. In that same quiet centre motion becomes the second clue. Stars move faster as they pass near the deepest point. Their orbits are not perfect circles. They are ellipses that precess in slow drift. The drift can be small. The pattern can still carry meaning. A cluster core can look like a smooth glow. Inside that glow, countless points trace short arcs. The arcs overlap like threads in a dark fabric. The fabric is calm, the tension is real. A payoff arrives in the pattern. If the speed rises in a way that matches a single central mass, the centre can be compact. If the speed rises without a compact source, the mass can be spread out. The difference is not loud. It is a subtle change in curvature of motion. The idea of influence sets a gentle radius. Within it, the central mass dominates. Outside it, the shared pull of the cluster takes over. The influence radius is not a hard ring. It is a gradient. The gradient is the third physical detail. The density of stars can rise toward the centre. The rise can be steep or shallow. A steep rise can hint at a compact anchor. A shallow rise can hint at many bodies sharing the weight. In a calm scene, the centre of the cluster looks like a faint lantern made of starlight. The outer region looks like sparse dust. The inner region looks like layered mist. The mist is made of overlapping tracks. Each track is an orbit that repeats over time. Another payoff arrives in a simple relation. More central mass means tighter orbits for the same distance. Tighter orbits mean shorter orbital times. Shorter times mean more mixing of stellar paths. Over long eras that mixing can smooth the core, it can also heat the cluster by gravitational encounters. The middle mass black hole can sit as a silent heater. It does not need bright gas to have an effect. It only needs to be heavy and compact. One number anchors the scale. An intermediate mass black hole can be about 10,000 times the mass of the Sun. That is like a pile of 10,000 coins compared with a single coin. The pile is still small beside a mountain of coins, yet it is far heavier than a handful. This scale shift is gentle but important. It moves from a single star to a crowd of stars. It still stays far below the masses found in galactic centres. The middle range can act like a stepping stone. It can also act like a trap. In a cluster, repeated encounters can drive objects inward. The inward drift is slow. It can take many cluster lifetimes. The drift increases density in the core. Density raises the chance of close passages. Close passages exchange energy. Some stars are pushed outward, some sink inward. The central region becomes a quiet engine of rearrangement. A visual anchor holds the idea in place. Near the center, a dark point is not seen. Instead, a tight knot of orbits is seen in motion. The knot looks like a braided cord. Each strand is a star path. The braid thickens toward the middle. The braid also twists faster there. The twist is not a spin of a surface, it is a change in orbital frequency. The braid suggests a compact anchor even when the anchor is invisible. A small payoff sits inside that image. The braid cannot form without a central focus. A distributed mass makes a softer pattern. It makes a fuzzier core with less coherence in tight loops. Limits appear soon after. Observation faces crowding in the core. Many stars overlap along the same line of sight. Many orbits cross in projection. A signal would blend with other signals. The true motion can be hidden by chance alignment. In addition, random encounters jostle orbits. The jostling adds noise to any inferred mass. Models also face degeneracy. A cluster with many dark remnants can mimic a single black hole. A compact central object can be confused with a dense swarm of smaller objects. The limit is not a lack of imagination. It is a limit of resolution and indirect inference. The center is too crowded. The timescales are too long. The clues are subtle shifts in distributions. Another visual anchor softens the limit. The cluster core becomes a fog of faint points. The fog has a brighter center. The brightness falls outward in a smooth gradient. Inside the gradient, the fastest stars spend little time near the middle. They rush through pericenter. They linger near apocenter. The lingering shapes the light profile. The profile becomes a record of motion. A payoff arrives with that record. Even when individual paths are unclear, the overall distribution can still constrain a central mass. The constraint is not exact. It can still narrow the possibilities. It can separate a compact anchor from a diffuse one. Time provides the final scale shift. A single orbit can take years or longer. The cluster itself evolves over millions of years. The question of a missing link stretches across billions of years. In that long span, intermediate masses can seed growth. They can merge with other black holes. They can drift toward larger structures. They can also remain locked in clusters that survive. The same quiet boundary remains the defining feature. The event horizon sets the sharpest edge in nature. It does so without showing a surface. The section ends with a calm promise. The next steps move from the idea of a hidden middle mass to the ways it can form. The scene shifts from braided orbits to the slow building of mass in dense stellar environments. A cluster can look peaceful while it quietly builds something far heavier than any single star. Intermediate mass black holes can grow in dense clusters through repeated mergers and slow inward drift. In that region, gravity acts like a gentle sorting process. Heavy objects tend to lose orbital energy. They sink toward the center. Lighter stars gain energy. They drift outward. This process is mass segregation. It is not a force by itself. It is an outcome of many small encounters. The center becomes a place where close passages are more common. The core grows denser over time. The density has a physical signature. The light profile steepens toward the middle. The stellar motions become more tightly curved. The inner orbits show smaller loops and quicker turns. A visual anchor settles the scene. A spherical cluster hangs in darkness. The outer stars form a wide halo. The inner region looks like layered mist. The mist thickens toward a dim nucleus. The nucleus is not a point of light. It is a place where paths overlap. The overlap creates a smooth glow. Inside that glow, the fastest stars pass through like brief streaks. The first payoff is simple. If heavy remnants concentrate, the chance of mergers rises. The center becomes a workshop without sparks. Black holes and dense remnants meet more often there. The meetings are guided by gravity alone. Encounters exchange energy. Some pairs bind, some are broken apart. Over many repeats, a durable pair can form. When a bound pair tightens, it can merge. The merged object becomes heavier. A heavier object sinks even more efficiently. The workshop gains a heavier tool each time. An everyday analogy frames the idea. It resembles a jar of mixed grains that is shaken slowly. Larger grains settle, smaller grains rise. The jar does not decide. It responds to many tiny collisions. The same quiet logic applies in the cluster core. The cluster is the jar, the encounters are the shakes of the heavier remnants of the larger grains. The center becomes a reservoir of heavy mass. Another payoff arrives with the idea of runaway growth. Once a remnant becomes heavy enough, it draws more encounters. It gains companions more easily. It merges more often. The growth can accelerate without any bright sign. The mass climbs step by step. The second concept enters in plain form. A core collapse is a contraction of the cluster center. It is not a collapse into a point. It is a gradual tightening of the inner region. The inner density increases. The encounter rate rises again. This tightening can happen over long spans. A scale shift makes the timeline gentle. A single close passage lasts hours or days. The core evolution can take millions of years. The cluster itself can persist for billions of years. In that long arc, small changes compound. The center becomes denser. The bound pairs become more common. The mergers become more likely. One number anchors the middle scale. A dense core can pack about 1 million stars into a region only a few light years across. That is like placing 1 million grains of sand inside a single small room. The comparison keeps the scale familiar. The physical consequence remains cosmic. In such crowding, gravity fields overlap. Tidal effects become more frequent. Orbits are perturbed often. The center becomes dynamically warm. The warm state is motion. It is not temperature in the usual sense. A visible detail carries that warmth. The velocity dispersion rises toward the middle. It means stars have a wider spread of speeds there. The spread shapes the inner light in motion. The third concept stays quiet and limited. 3-body encounters can harden a binary. A third object can carry away energy. The binary tightens. The tightening raises the chance of merger later. The process resembles a knot being pulled tighter each time a loose end is tugged. The knot is the binary, the tug is the encounter. The pulling is done by gravity exchange. The knot image is a new anchor of intuition. It explains why tightening can happen without friction. It also explains why the cluster can heat while the binary hardens. Another visual anchor appears to keep the rhythm. Near the center, 2 dark remnants circle each other. Their orbit is too small to be seen directly. The surrounding stars trace wider arcs. Each close pass slightly shifts the pair. The pair becomes tighter after many visits. The surrounding arcs become subtly different. The core looks the same in brightness. The hidden structure changes within. A limit of observation arrives softly. The central process is inferred, not watched. The densest region is crowded in projection. Many stars overlap along the same line of sight. Motions are measured as blended signals. Small changes can be masked by noise. Models also share a limit. A cluster with many heavy remnants can mimic a single heavier object. The inferred central mass can be biased by assumptions about unseen populations. The limit is a degeneracy between a compact black hole and a dense swarm. It is also a limit of time. The growth happens over spans longer than any direct monitoring. The evidence is a snapshot. The story is reconstructed from distributions. Another payoff resolves a small question. Even with degeneracy, certain signatures help. A compact central mass tends to create a sharper rise in speeds very near the center. Diffuse population creates a smoother gradient. The difference is not absolute. It can guide probability. It can narrow the range of central mass. The section ends with a gentle transition. The next step moves from cluster dynamics to the role of gas and collapse paths. The view shifts from crowded orbits to the slow inward flow that can build a heavier seed. A heavy seed can form without a crowd of stars if a gas cloud stays smooth as it falls. Intermediate mass black holes can begin when a dense cloud collapses without breaking into many stars. In that region, gravity competes with pressure and rotation. The cloud is not a uniform ball. It has layers. It has a temperature gradient. It has a slow spin that reshapes the fall. The first physical detail is the shape of the flow. Material spirals inward. It forms a thick disk with a rounded edge. The edge is not sharp. It is a fading boundary where the density drops. Inside the disk, an inward drift continues. The drift is slow compared with freefall. The disk can feed a central object by shedding angular momentum. Angular momentum is resistance to changing rotation. It is like the way a rolling hoop keeps its spin. The cloud needs a way to move that resistance outward. The inward path opens when the resistance is transported away. The central region then becomes denser. The density rises toward a compact core. A visual anchor settles the scene. A dark cloud hangs in space like a quiet ink stain. Toward its center, the stain becomes darker. The middle shows a faint ring of warmer gas. The ring is not bright. It is a thin glow that traces a slow spiral. Around the ring, cooler layers wrap like soft bands. The bands slide inward, then flare outward in gentle waves. A payoff arrives in the behavior of fragmentation. A gas cloud often breaks into clumps. Each clump can become a star. When the cloud stays warm enough, clumps struggle to survive. Pressure smooths small over densities. The cloud behaves more like one continuous sheet. The collapse then keeps its mass together. The path toward a heavier seed becomes possible. An everyday analogy frames the idea. It resembles thick porridge on a slow turntable. Small bumps flatten as the surface slowly swirls. The porridge still flows inward if the center is lower. The flow stays continuous instead of breaking into many droplets. In the cosmic cloud, the center is the lower point in gravitational potential. The smoothing is done by pressure and heat. The swirl is done by rotation. The second concept enters with a short definition. Accretion is gradual growth by collecting surrounding matter. It is not a sudden event. It is a steady transfer. In the disk, accretion is guided by frictional effects inside the gas. The gas is not perfectly smooth. It has turbulence. It has waves. It has magnetic stresses. These stresses act like a slow conveyor. They move angular momentum outward. Material can then move inward. Another payoff resolves a question about why the disk matters. The disk prevents a quick pile-up that would stall the collapse. It provides a route for mass to reach the center. The disk also sets a sail for the final object. A thicker disk can feed a larger seed before it thins out. A thinner disk may starve the center earlier. The third concept remains gentle and limited. Radiation pressure can push back on infalling gas. Light behaves as a force when it is trapped. When the center grows hot, it shines. The shine can slow the fall. The outcome depends on balance. If cooling is efficient, the cloud fragments. If cooling is suppressed, the cloud stays smooth and heavy. The physical detail is in the gradient. Temperature rises toward the center. Opacity can rise with density. The inner region can trap heat. Trapped heat can inflate the disk. The disk becomes puffed up. Its thickness is a signature of pressure support. One number anchors the scale in a safe way. A collapsing cloud can begin with about 100,000 times the mass of the Sun. That is like 100,000 pebbles compared with a single pebble. The number is not a final black hole mass. It is an available reservoir. Only part reaches the center. Yet even a fraction can produce a middle mass seed. The scale shift becomes calm and wide. A disk spans light days or more. The collapse unfolds over thousands of years or longer. The resulting black hole can persist for billions of years. The long persistence makes the beginning hard to witness directly. A limit of observation arrives softly. The central collapse is hidden by surrounding gas. The region is opaque at many wavelengths. The details depend on models of cooling, turbulence, and transport. Different assumptions can change where the fragmentation happens. The limit is not only resolution, it is also the indirect nature of inference. A signal would arrive as a faint spectrum and a broad profile. Many different structures can produce similar profiles. The early phase can also be brief compared with cosmic time. A short phase is easy to miss in any survey. Another visual anchor keeps the rhythm. The disk shows a slow ripple pattern. Spiral arms appear as density waves. They are not rigid structures. They are moving compressions. Gas enters a spiral arm, it compresses. It heats slightly, it exits and cools. The spiral pattern can carry angular momentum outward. The pattern acts like a gentle hand that turns the disk. A payoff arrives in that mechanism. The spiral waves provide a pathway for inflow without needing discrete clumps. The collapse can proceed while remaining smooth. The central object can grow quietly. It can cross into the intermediate mass range if feeding continues long enough. The section ends with a soft transition. The next step moves from formation paths to the ways these objects reveal themselves. The view shifts from a hidden disk to the subtle traces in surrounding light and motion. Sometimes an invisible mass leaves its clearest trace not in light but in timing. Intermediate mass black holes can be inferred when stars and gas respond in repeatable gravitationally set patterns. At this distance, the scene begins as a quiet stellar field with no obvious center. A faint haze marks a dense region. The haze thickens inward. Individual points blur together. The first physical detail is motion. Some stars trace tighter loops near the core. Their paths curve more sharply. Their speeds rise subtly. The change is not dramatic in any single star. It appears as a trend in many stars. The trend forms a profile. The profile becomes a fingerprint of central mass. A visual anchor holds the idea. The core looks like a soft whirlpool of faint points. No bright spiral is seen. Instead, the density rises like fog near a lake at night. The fog has a smooth gradient. The gradient is steepest toward the center. Stars near that center seem to flicker in position. The flicker is the projection of many overlapping arcs. A payoff arrives in a simple inference. A compact central object produces a stronger rise in speed at small radius. A diffuse swarm produces a gentler rise. The difference answers a small question. Is the center dominated by one compact mass, or by many smaller masses sharing the load? This is the first checkpoint. It turns a hidden object into a measurable hypothesis. The second concept enters with a short definition. Velocity dispersion is the spread of speeds in a group. It is not a single orbit speed, it is a statistical width. In the core, velocity dispersion tends to rise. The rise can signal a deeper potential well. The potential well is the third concept. It is the depth of gravitational energy per unit mass. It is not a hole in space, it is a map of how hard it is to escape. The map is read through motion. Motion is read through light shifts and positional change. An everyday analogy frames the core. It resembles a bowl of marbles on a shallow dish. Marbles near the center roll faster. Marbles near the rim drift slowly. The dish is not seen. Only the marble motion is seen. From that motion, the dish shape is inferred. The analogy stays gentle and concrete. It also carries a payoff. The same motion pattern can reveal whether the dish has a deep pit at the center. A deep pit stands for a compact black hole. A shallow dip stands for distributed mass. Another visual anchor arrives to keep the rhythm. In the core haze, a few bright points stand out. Their paths traced over time make elongated loops. The loops share a common focus. The focus is not a visible object. It is a location that many orbits respect. The loops precess slowly. Their major axes rotate over long spans. The precession is a subtle physical detail. It can hint at the mass distribution. A concentrated mass makes precession behave differently than an extended one. A payoff sits in that behavior. Precession can break some degeneracies. It provides extra information beyond a simple speed profile. One number anchors the scale in a safe way. The sphere of influence of a middle mass black hole can be about 1 light year across in a dense cluster. That is like the distance light travels in 1 year, compared with a small neighborhood of stars. The number is not a sharp boundary. It is a region where the central mass dominates the motion. Inside that region, orbits feel the compact pull more strongly. Outside it, the cluster's shared gravity takes over. The scale shift remains calm. A single orbit can take years. The core's structure changes over millions of years. The black hole can persist for billions of years. The trace is a momentary snapshot. The cause is a long-lasting anchor. A limit of observation arrives softly and clearly. The core is crowded. Many stars overlap in projection. Measurements blend. Proper motions are small on the sky. Spectral shifts can be seen. Unresolved binaries can mimic higher dispersions. Stellar remnants can be unseen and numerous. Models must assume a distribution of unseen masses. Different assumptions can fit the same data. The limit is a degeneracy in inference. It is also a limit of resolution. The sphere of influence can be comparable to the smallest resolvable region. A signal would carry the truth, but the signal is mixed with others. Another payoff resolves what can still be done. Statistics can help. A full distribution of velocities can be compared to simulations. Radial trends can be matched. The presence of a central compact mass can be tested by how sharply the dispersion rises at the smallest radii. The test is not perfect. It is still a path to probability. The section closes with a final visual anchor. The core haze is seen as layered brightness. The brightest layer sits at the center. The layers fade outward. The motion within those layers remains smooth and unhurried. The next step moves from stellar motion to gas behavior and brief flares. The view shifts from long arcs to transient signatures that can also betray a hidden middle mass. A brief flare can act like a lantern that turns on for a moment in an otherwise quiet place. Intermediate mass black holes can reveal themselves when tidal forces reshape a passing star into a stream of glowing debris. At this distance, the scene begins as a calm stellar field near a dense core. A single star drifts along an elongated orbit. The orbit passes close to an unseen center. The first physical detail is the tidal gradient. Gravity is stronger on the near side of the star, it is weaker on the far side. The difference stretches the star. The stretch is not gradual forever. There is a threshold. Past that threshold, the star cannot hold its shape. The threshold is the tidal radius. It is the distance where tidal forces overcome self-gravity. The star is pulled into a long ribbon. The ribbon wraps around the dark center. It forms an arc of debris. The arc narrows into a stream. The stream has a density gradient along its length. The densest part leads, the thinnest part trails. A visual anchor holds this moment. A pale curved filament circles an invisible point. The filament glows faintly at first. It brightens where the stream collides with itself. A soft ring-like shape forms. It is not a perfect circle. It is a warped loop. The loop sits inside a darker halo. The halo is made of diffuse gas and scattered light. Light behaves as a tracer of heat. Heat concentrates where the stream compresses. That compression becomes the first payoff. A tidal disruption does not need an event horizon to be seen. It needs a stream that shocks and heats. The glow answers a small question. How can an unseen object announce its presence without a persistent beacon? The answer is timing and geometry. The flare rises. It peaks. It fades. The rise and fade reflect the return of debris. The returning debris falls back toward the center. Not all debris escapes. Some remains bound. It swings out then returns. The return rate shapes the light curve. The second concept enters with a short definition. A light curve is brightness over time. It is a simple record. It can carry hidden structure. The record can suggest the mass of the central object. A heavier object has a stronger tidal field at a given distance. It can disrupt at a wider range of pericenter distances. It can also set shorter or longer fallback times depending on the orbit. The third concept stays narrow and calm. Circularization is the settling of debris into a rotating flow. It is not instant. Debris initially follows elongated paths. Streams intersect, they collide. Energy is lost as heat. Angular momentum is largely kept. The debris then settles into a disk-like configuration. The disk has an inner edge. It has an outer boundary where the debris supply thins. It also has a temperature gradient that rises inward. This gradient creates a spectrum that shifts over time. Another payoff arrives in the shape of the flare. A rapid rise followed by a slower decline suggests a sudden injection and gradual feeding. Small bumps can appear when streams self-intersect in different places. Those bumps can answer a second small question. Is the debris settling quickly, or does it take many orbits to settle? The answer influences how the flare looks. It also influences whether the event is long-lived. One number anchors the scale in a safe way. The brightest phase can last about a few months. That is like a seasonal change compared with the slow life of a star. The comparison keeps the time familiar. The scale shift is gentle. The disruption itself occurs over hours. The light can persist for months. The remnant configuration can affect the core for far longer. In the long view, such events are rare in any single cluster. Yet across many clusters and many galaxies, a few appear. The rarity itself becomes part of the inference. Another visual anchor arrives to keep the rhythm. The debris stream forms a thin crescent. The crescent thickens into a warped band. The band shows a brighter knot where shocks concentrate. Outside the knot, the band fades to a smooth glow. The knot drifts slowly along the band. The drift reflects orbital motion. The band remains centered on an invisible focus. A payoff sits inside this picture. The focus is compact, the stream wraps tightly. A diffuse mass would not produce such a coherent ribbon. The coherence points back to a concentrated potential well. Limits arrive softly and clearly. A flare can be confused with other transient phenomena. Spectral shapes can overlap. Dust can absorb and redden light. Gas around the core can reprocess emission into different bands. The brightest region may be hidden behind opaque material. Models must assume how much debris becomes bound. They must assume how efficiently the debris circularizes. Different assumptions can fit the same light curve. The limit is an ambiguity in interpretation. It is also a limit of sampling. If brightness is measured sparsely, the true peak can be missed. A signal would carry the history, but the record can be incomplete. Another payoff resolves what still can be learned. The combination of timescale and peak brightness can constrain mass ranges. The presence of broad emission lines can hint at fast-moving debris. The fading pattern can suggest fallback behavior. None of this is definitive alone. Together it can elevate a candidate. It can identify a hidden middle mass object that deserves deeper study. The section closes with a gentle transition. The next step moves from brief flares to longer-lived faint accretion signatures. The view shifts from a glowing ribbon to a steady dim swirl that can also reveal intermediate mass black holes. A steady dim glow can be more revealing than a rare flare, because it carries a long memory. Intermediate mass black holes can be suggested by faint accretion that shapes a persistent structured spectrum. In that region, gas is not abundant. It is thin, it is patchy, it drifts through a crowded gravitational field. The first physical detail is the flow geometry. A rotating disk forms if gas has enough angular momentum. The disk is not always thin. It can be puffed up. It can resemble a thick torus with a soft inner rim. The rim is set by intense gravity and heating. The outer edge fades into a diffuse envelope. The disk shows a temperature gradient. The inner region is hotter. The outer region cools smoothly. Light behaves as an index of that gradient. Hotter zones tend to emit higher energy radiation. Cooler zones emit softer light. A visual anchor settles the scene. A dim smoke-like swirl hangs around an unseen center. The swirl is not bright enough to dominate the scene. It sits as a faint oval haze. The haze has a brighter crescent on one side. The crescent marks where the flow is denser. The center of the oval is darker. It is not empty space. It is a region where light paths are bent and trapped. The faint structure stays stable for long spans. It shifts slowly as the supply changes. A payoff arrives in the idea of persistence. A long-lived low-level glow suggests continual feeding. It answers a small question. Can a hidden object be found without a dramatic event? The answer is yes if the flow leaves a stable signature. The signature is not a single line or peak, it is a shape across wavelengths. The second concept enters with a short definition. An accretion spectrum is light spread across energies. It reflects temperatures and processes in the flow. In a simple disk, a range of temperatures produces a broad continuum. In a more complex flow, additional components appear. Some photons scatter off hot electrons. Scattering can harden the spectrum. The physical detail is in the slope. A steep slope suggests cooler emission. A flatter slope suggests stronger scattering. The third concept stays narrow and calm. An accretion rate is the amount of mass falling inward per time. It controls luminosity in a broad way. It also controls how thick the flow becomes. A higher rate can thicken the disk. A lower rate can make it more tenuous. The effect appears as changes in brightness and hardness. Another payoff arrives with variability. Even faint accretion can flicker. The flicker timescale can relate to size. Smaller regions can vary faster. Larger regions vary more slowly. This connects mass to timing. A heavier black hole has a larger characteristic scale. Its inner regions are larger in absolute size. The same relative processes then occur on longer absolute times. One number anchors the idea safely. A brightness variation might repeat on about 1 day. That is like the rhythm of a night and a morning compared with the long age of a cluster. The number is not universal. It is a reference scale for the inner flow. A day scale hints at a compact region that is not too small. It can be consistent with an intermediate mass depending on context. The scale shift remains gentle. The inner flow changes over hours to days. The feeding supply can drift over years. The host cluster evolves over millions of years. The black hole persists over billions of years. The faint glow is a brief whisper in that long history. Another visual anchor keeps the rhythm. The disk edge shows a subtle bright ring. The ring is not sharp. It is a gradient of emission. Within the ring, a darker notch appears where the flow is thinner. The notch can move slowly with time. It's like a gap in a fog bank that opens and closes. The gap suggests inhomogeneity in the supply. The pattern carries a payoff. Even weak emission can reveal structure in the flow. It can separate disk like emission from diffuse hot gas. It can also hint at a compact central well. Limits arrive softly and clearly. Faint accretion is difficult to attribute. Other compact objects can also glow weakly. A dense cluster can produce background emission from many sources. Dust and gas can absorb and reshape the spectrum. The true luminosity can be underestimated. The distance can be uncertain. The limit is partly confusion. It is partly modelling. Different accretion models can fit similar spectra. Variability can be sparse in time coverage. A signal would be clearer with continuous sampling, but sampling is often incomplete. Another payoff resolves what still stands out. The combination of low luminosity and a disk-like continuum can be suggestive. The presence of a broad, smooth component with a consistent hardness can favour a larger accretor. The variability timescale can further constrain size. None of these alone proves a middle mass black hole. Together they build a stronger case. The section closes with a gentle transition. The next step moves from electromagnetic whispers to gravitational ones. The view shifts from faint, steady swirls of light to the quiet ripples that merging masses send across space-time. A quiet ripple can carry the weight of an unseen merger across a vast emptiness. Intermediate mass black holes can be supported by gravitational waves when merging masses land in the middle range. In that region, space-time behaves like an elastic medium in a slow, subtle sense. The medium does not resist, it transmits. A merger begins as two compact objects in orbit. The orbit shrinks gradually. Energy leaves as waves. The waves do not need light. They carry information in timing and frequency. The first physical detail is the waveform shape. It begins as a slow chirp. The chirp rises in pitch. It rises in amplitude. Then it ends in a soft ring down. The ringdown is a damped vibration of the final black hole. It fades like a struck bell that is muffled. The bell image is an everyday analogy. It stays gentle and unique here. It explains why the end has a characteristic tone. The tone is set by mass and spin. The merger is not seen. Its imprint is heard in the pattern of change. A visual anchor holds the invisible event in a calm picture. Two dark points orbit in a wide empty field. Their paths draw an oval. The oval tightens into a circle. The circle shrinks into a tight spiral. Around them, faint concentric ripples spread outward through space-time. The ripples are not shape in gas. They are distortions in distance. Light behaves as usual while the ripples pass. A signal would arrive earlier and later by tiny amounts if compared across paths. The first payoff arrives in the idea of a scale marker. The frequency of the chirp depends on the orbital timescale. The timescale depends on mass. Heavier systems orbit more slowly near merger. That means the chirp can sit lower in frequency. When a chirp sits between typical stellar mass and supermassive patterns, it suggests a middle mass system. This resolves a small question. How can a mass be estimated without a picture? The answer is in the rhythm. The waveform is a clock. Its tick rate changes predictably. The second concept enters with a short definition. Chirp mass is the mass combination that sets chirp evolution. It can be inferred from how frequency rises. It is not the same as total mass. It is closely related. The concept stays minimal. It is only used to connect timing to mass. The third concept remains calm and narrow. Ringdown is the fading vibration of the merged black hole. It carries the final object's properties. It is a short tail in time. It is a long tail in meaning. It can confirm that the final object is a black hole. It can also constrain its mass range. Another payoff arrives in the transition from inspiral to ringdown. The inspiral follows a predictable sweep. The ringdown follows a predictable decay. Together they form a coherent story. The middle mass claim is stronger when both parts align. When only part is seen, ambiguity grows. One number anchors the scale gently. The strongest part of a merger signal can last about 1 second for a middle mass system. That is like a single breath compared with the long orbiting history before it. The scale shift is soft. The binary can orbit for millions of years before merger. The final second carries the loudest ripple. The ripples then cross the universe for billions of years. The arrival is brief. The origin is ancient. This shift in time helps the event feel calm rather than sudden. The physical details within the signal remain concrete. Frequency rises smoothly. Amplitude rises smoothly. The waveform ends in a fading ring. The fading ring has a characteristic decay time. The decay is tied to the size of the horizon region. A larger black hole has a longer characteristic time. The horizon itself is not directly observed. The ringdown is a proxy for that boundary. Another visual anchor appears to keep the rhythm. After the merger, one dark point remains. Around it, space-time ripples form expanding shells. The shells thin as they spread. The shells become harder to distinguish from quiet space-time. The shells do not carry material. They carry geometry. Their passage leaves no lasting mark in empty space. The quiet returns. The payoff is in the cleanliness. Gravitational waves pass through intervening matter with little alteration. That helps reduce certain confusions. The signal shape can be preserved across vast distances. Limits arrive softly and clearly. Gravitational wave signals can be weak. Noise can mimic parts of a chirp. Multiple sources can overlap. Parameter estimation can have degeneracies. Mass and spin can trade off in fits. The distance can be uncertain. The orientation can be uncertain. The limit is not only sensitivity, it is also modelling of waveform families. Small modelling errors can bias inferred masses. In addition, an intermediate mass claim can rest on the tail of a distribution. It can be sensitive to priors. A signal would be clearer with multiple detectors and better low-frequency coverage, but coverage is finite. Another payoff resolves what remains robust. The presence of a ring down with a frequency consistent with a large final mass can strongly support a black hole. The match between inspiral and ring down can constrain the total mass range. Repeated detections can also build population evidence. If several events cluster in the middle mass regime, the missing link becomes less missing. The section closes with a gentle transition. The next step moves from mergers to the environments that produce them. The view shifts from ripples in space-time to the quiet habitats such as clusters and dwarf galaxy cores where intermediate mass black holes may reside. A small galaxy can look like a quiet smear of light while it carries a deep secret at its center. Intermediate mass black holes may live in dwarf galaxies and leave traces in the way stars and gas settle. In that region, gravity is shared between a diffuse halo and a compact core. The first physical detail is a gradient in stellar density. The center can be slightly brighter. The brightness can rise smoothly toward a tiny nucleus. The rise can be steep enough to suggest a concentrated mass. Yet the outer regions remain faint and extended. The galaxy's light looks like a soft oval. Its edges fade into darkness with no sharp boundary. A visual anchor settles the scene. A dwarf galaxy floats as a pale, elongated cloud. Near its center, a small knot of light sits like a dew bead on a leaf. The bead is not a point source. It is a dense cluster of stars. Around it, a thin veil of starlight spreads outward. The veil shows subtler symmetry. One side is slightly more stretched. That stretch hints at tides from a larger neighbor. The first payoff arrives in the role of a nucleus. A compact nucleus can act as a container for a middle mass black hole. It answers a small question. Where can such a black hole hide if not in a giant galaxy? The answer is a compact core inside a small system. The core can be dense enough to seed growth. It can also preserve an early remnant. The second concept enters with a short definition. A tidal radius is the distance where external tides strip material. It is not a physical wall, it is a threshold in binding. In a dwarf galaxy near a larger one, the outer stars can be stripped. The center can survive longer. Stripping leaves streams. Those streams are physical details in the stellar distribution. They appear as faint linear extensions, they appear as arcs. They can form a trailing tail and a leading tail. The tails are not uniform. They show clumps and gaps. A payoff arrives in the geometry of those tails. A more compact central potential can keep inner stars bound. It can make the tails begin farther out. It can also change the velocity pattern along the tail. The tail then becomes a map of the inner mass. The third concept stays narrow and calm. A velocity dispersion profile is how the spread of speeds changes with radius. In a dwarf galaxy, this profile can remain flat or rise toward the center. A rising center can suggest a compact mass. The profile is read through many stars. Individual stars can be misleading. The population trend matters. Another visual anchor keeps the rhythm. Near the nucleus, a few bright stars trace small arcs over time. Farther out, stars drift in broader paths. The inner arcs appear tighter and more curved. The outer paths look more like gentle sweeps. The pattern resembles ink spreading in water, but with a denser droplet at the center that resists mixing. The ink image is the everyday analogy here. It stays unique in this script. The droplet stands for the compact nucleus. The spread stands for the diffuse galaxy. The analogy carries a payoff. A compact central mass slows the diffusion of orbits. It keeps the nucleus tighter. It also shapes how the outer stars are peeled away by tides. One number anchors the scale gently. A typical dwarf galaxy can contain about 1 billion stars. That is like a jar holding 1 billion grains compared with a much larger jar holding far more. The number gives perspective without needing detail. The scale shift remains calm. A nucleus spans a few light years. The galaxy spans thousands of light years. The interaction with a larger neighbor unfolds over billions of years. The tail can be drawn over hundreds of millions of years. The present view is a single frame in a slow dance. Physical details continue in gas even when faint. If gas is present, it can form a thin disk or a patchy cloud. The gas can show rotation. The rotation curve can flatten. Near the center, a compact mass can create a sharper rise. The rise would be seen as a steeper gradient in orbital speed. A signal would show a central kink. The kink is subtle. It is often drowned by turbulence and low gas density. Another payoff resolves how multiple clues can combine. A rising stellar dispersion near the center, plus a compact nucleus plus a subtle rotation kink, can point toward an intermediate mass black hole. The case is strongest when different tracers agree. Each tracer alone can mislead. Together they narrow possibilities. Limits arrive softly and clearly. Dwarf galaxies have few bright tracers. Sampling is sparse. Distance uncertainties can blur inferred masses. Anisotropy in stellar orbits can mimic a central mass. A dense cluster of ordinary remnants can also mimic one black hole. Tidal stripping can heat the system and inflate dispersion. The limit is both observational and modelling. It is hard to separate tides from a central compact object. It's also hard to resolve the inner few light years at large distances. A signal would improve with sharper resolution, but resolution is finite. Another visual anchor arrives to keep the rhythm. The dwarf's tail appears as a faint ribbon of stars. The ribbon arcs gently. It fades into the background. The nucleus remains as a persistent knot. The knot holds its shape while the ribbon stretches. The payoff sits in that contrast. A resilient knot suggests a deep binding energy. A shallow potential would dissolve more easily. The section closes with a gentle transition. The next step moves from small galaxies to star clusters as long-term sanctuaries. The view shifts from tidal tails and nuclei to the dense ancient clusters where intermediate mass black holes may remain quietly embedded. An old cluster can keep a secret for billions of years by looking almost unchanged. Intermediate mass black holes may remain embedded in ancient star clusters and shape their cores in subtle, persistent ways. In that region, the cluster is not a simple ball of equal stars, it is a layered system. The outer halo is sparse, the inner core is crowded. The first physical detail is the core profile. Brightness rises toward the center. The rise can be steep or shallow. The inner slope is a clue. A compact central mass tends to maintain a smoother, broader core by stirring the center. A purely self-gravitating core can contract more strongly. The difference is not dramatic in a single image. It appears in the gradient of light and in the distribution of stellar speeds. A visual anchor settles the scene. The cluster hangs as a faint sphere of points. The outer edge fades like mist. Toward the center, the points blend into a soft glow. Within that glow, a slightly darker pocket appears. The pocket is not empty. It is a region where the density changes shape. Around the pocket, the brightness forms a gentle ring of higher intensity. The ring is not sharp, it is a slow transition. The ring suggests that stars spend time at certain radii. Their orbits linger there. The first payoff arrives in the idea of dynamical balance. A central black hole can act as a long-term heat source. It injects energy through encounters. That energy prevents extreme core collapse. This answers a small question. Why do some clusters retain extended cores instead of contracting into very dense centers? The answer can be the presence of a compact mass that redistributes orbital energy. The second concept enters with a short definition. Relaxation is gradual mixing of orbits by many encounters. It is not a single collision, it is a slow drift of energies. In an old cluster, relaxation has time to work. Heavy objects sink, light objects drift outward. The core becomes the meeting place. The third concept stays narrow and calm. An influence radius is where the black hole dominates motion. It is not a visible boundary. It is a region of stronger curvature and orbits. Inside it, the velocity of dispersion tends to rise. The rise can be mild but systematic. Another payoff arrives in the pattern of ejections. Close encounters in the core can fling some stars outward. The core then loses some mass. It can maintain a steady size. That steady size can persist across long spans. It becomes a fossil record of the internal engine. The physical detail is in the distribution of stellar paths. Near the center, orbits are tighter. The pericenters are small. The apocenters cluster around a core scale. This creates a subtle cusp or a flat core depending on the energy flow. An everyday analogy frames the cluster core without using people or machines. It resembles a pot of thick soup cooling on its own. The surface looks still. Inside, gentle convection keeps the center from becoming too cold. The convection is not visible as waves. It is inferred from the stable temperature profile. In the cluster, the profile is the light and speed distribution. The convection stands for energy exchange through encounters. It keeps the core from becoming too sharply peaked. The analogy carries a payoff. A stable core does not mean nothing happens. It can mean constant small mixing. Another visual anchor keeps the rhythm. The inner glow shows faint striations. The striations are not lines. They are slight variations in density. They appear as layered shells when averaged over many stars. The shells are not physical walls. They are statistical layers in orbital occupancy. A compact central mass can create a distinct change in slope at a certain radius. That change is a physical feature in the profile. It is a kind of knee in the brightness gradient. One number anchors the timescale gently. An ancient cluster can be about 10 billion years old. That is like 10 billion heartbeats compared with a single heartbeat but stretched into cosmic time. The number emphasizes persistence without needing precision. The scale shift remains calm. Individual encounters last hours or days. Orbits take years. Relaxation unfolds over millions of years. The core structure persists over billions of years. The cluster becomes a quiet archive. Another payoff resolves how an archive can be read. Even if the black hole is invisible, its influence can be inferred from statistics. The distribution of velocities near the center can hint at a deeper potential well. The distribution of stellar densities can hint at energy injection. The presence or absence of a steep cusp can hint at central heating. None of these is decisive alone. Together they provide a coherent pattern. Limits arrive softly and clearly. Cluster cores are crowded. Stars overlap in projection. Unresolved binaries can inflate velocity dispersion. Dark remnants can accumulate and mimic a central black hole. Mass-to-light ratio can vary with radius and confuse inferences. Models must assume a distribution of unseen objects. Different assumptions can reproduce similar light profiles. The limit is degeneracy in modeling and limits of angular resolution. The influence radius can be smaller than the resolvable core. A signal would be clearer with deeper sampling of motions, but sampling is finite. Another payoff resolves what can break the degeneracy. Proper motion measurements across many stars can reduce reliance on line-of-sight velocities alone. Comparing multiple clusters can reveal which core structures are unusual. If a cluster shows an extended core plus a rising central dispersion, the case strengthens. If the core is sharply collapsed with no rise, the case weakens. Population reasoning becomes a tool. Another visual anchor closes the section. The cluster's outer halo drifts as a sparse crown. The inner core remains a soft lantern. The lantern does not flicker strongly. It holds a stable glow. The stable glow suggests steady mixing. The next step moves from long-lived habitats to the broader role of intermediate masses as seeds. The view shifts from a single cluster core to the slow growth pathways that can lead toward the largest black holes. A seed becomes a giant through patience because gravity rewards steady supply over long time. Intermediate mass black holes can act as stepping stones towards supermassive black holes through growth and merging. In that region, three ideas stay enough. There is a seed mass. There is accretion as a steady inflow. There are mergers as occasional jumps. The first physical detail is the accretion structure. Gas that falls inward rarely drops straight. It tends to rotate. It forms a disk. The disk has an inner rim where temperatures rise. It has an outer boundary where the supply thins. The disk also has a gradient in density. Denser zones can form spiral compressions. These compressions drift and fade. They transport angular momentum outward. This transport allows mass to move inward. The inward path builds the seed. A visual anchor settles the scene. A dark center sits inside a broad, dim oval of gas. The oval is a disk seen at a tilt. One side looks brighter due to greater column density. Near the middle, a thin ring of higher brightness appears. The ring is not sharp, it's a soft band where heating is stronger. Around the ring, faint ripples trace spiral waves. The waves are slow, they are not violent shocks. They are gentle density patterns. The first payoff arrives in a clear connection. A stable disk can turn small amounts of gas into long-term growth. It answers a small question. How can a modest seed climb into a massive range without rare dramatic events? The answer is that steady feeding compounds. A small rate sustained for long spans can exceed a short burst. The second concept enters with a short definition. Accretion is growth by collecting surrounding matter. It is not guaranteed. It depends on supply and stability. The third concept is mergers kept simple. A merger is a union of two compact masses. It is a jump rather than a drift. In a rich environment, small seeds can merge. Each merge increases mass. Each increase deepens the potential well. A deeper well can attract more gas. This creates a feedback loop that is calm rather than explosive. Another payoff arrives in the idea of thresholds. Once a black hole becomes heavier, its sphere of influence grows. More nearby material can be bound. More orbits can be perturbed. This can channel gas inward. It can also increase the chance of interactions with other compact objects. The step from intermediate to larger scales becomes easier once the seed crosses a certain heft. One number anchors the scale gently. A supermassive black hole can reach about 1 billion times the mass of the Sun. That is like stacking 1 billion grains compared with a single grain. The number is vast. It is still a finite target. It implies that either the seed starts fairly large or the growth is efficient over time. The scale shift remains calm. Accretion can vary on days and years. Growth to extreme mass occurs over hundreds of millions of years. The universe provides that time. The seed stage can occur early. The giant stage can appear later. The middle mass stage is the bridge across that span. Another visual anchor keeps the rhythm. In a gas-rich region, filaments feed the disk. The filaments are narrow streams. They join the outer edge and wrap inward. Their edges are not clean. They show shear. Shear creates layered streaks in density. The layers slide past each other. The sliding dissipates energy. It helps gas settle into rotation. The payoff is in the geometry. The filament shape can deliver angular momentum and mass together. It can keep feeding stable without needing a sudden collapse. A limit of intuition arrives softly and clearly. Growth histories cannot be watched end to end. Only snapshots are seen at different cosmic times. Models must connect those snapshots. The connection depends on assumptions about gas supply and feedback. Feedback can heat gas and reduce inflow. Feedback strength is hard to estimate without direct measures. In addition, mergers can eject a merged black hole from a shallow potential. That possibility depends on recoil and environment. The limit is both observational and theoretical. It is hard to infer the exact path from seed to giant. Many different paths can produce similar end states. A signal would help if it captured both feeding and merging over long spans, but such a record is not available. Another payoff resolves what can still be concluded. Intermediate mass black holes remain plausible seeds because they reduce the required growth burden. Starting larger means fewer E-folds of growth are needed. Merging in clusters and small galaxy nuclei can provide early mass boosts. Steady accretion can then take over when gas is available. The bridge concept becomes concrete. A middle mass object can be heavy enough to survive disturbances. It can also be light enough to form in many environments. The section closes with a gentle transition. The next step moves from growth pathways to the consequences for galaxies and clusters. The view shifts from disks and filaments to the quiet, long-term imprint a growing black hole can leave on its surroundings. A growing mass can change its surroundings without ever becoming bright enough to dominate the sky. Intermediate mass black holes can reshape nearby gas and stars through long-term gentle feedback and gravitational stirring. In that region, the environment is a balance of binding and escape. Gas cools and settles. Gas also heats and expands. Stars orbit and mix. The first physical detail is a cavity in gas distribution. A faint central glow is surrounded by a slightly darker zone. The darker zone is not empty. It is lower density. It has a smoother texture. Around it, a thin shell of denser gas forms a soft rim. The rim can be ring-like. It can be incomplete. The rim marks where gas piles up after being pushed outward. A visual anchor settles the scene. A dim nebular haze hangs in a small galaxy core. At its centre, an oval hollow appears like a clear pool in fog. The pool has a soft edge. The edge brightens into a pale arc. Beyond the arc, the haze becomes patchy again. The patchiness forms clumps and filaments. The clumps drift. The filaments curve. They align loosely with the galaxy's rotation. The first payoff arrives in the meaning of the hollow. A compact object can heat gas near the centre. That heating can raise pressure. Higher pressure can slow inflow. This answers a small question. Why does some gas fail to reach the deepest centre even when gravity is strong? The answer can be that added heat changes the flow. The heat does not need to be explosive, it only needs to be persistent enough to keep gas slightly puffed up. The second concept enters with a short definition. Feedback is energy returned to surrounding material. It can come from radiation and outflows. It does not require visible jets in this calm framing. It can also come from shocks in the inner flow. The third concept stays narrow and calm. Binding energy is how strongly gas is held by gravity. A deeper potential well means higher binding, yet even a deep well can be resisted if pressure support rises. Pressure support is not a new concept here. It is a plain description. It is the gas pushing back. Another payoff arrives in the role of timescale. A brief flare might not move much gas. A steady, modest heating over long spans can. It can inflate the inner region slightly. It can create a stable hollow. It can also change where dense gas collects. That changes where new stars can form. The environment becomes structured by a quiet influence. An everyday analogy frames the process. It resembles warm air above a lake at dawn. The water surface is cool. A thin, warm layer forms above it. Fog density changes with small temperature differences. The centre of the lake can look clearer while the edges hold thicker fog. The analogy is gentle and unique here. The warm layer stands for persistent heating. The fog stands for gas density. The clearer pool stands for the cavity. The payoff is immediate. Small changes in energy can rearrange density without dramatic motion. One number anchors the scale gently. A cavity might span about 10 light-years across. That is like a small clearing within a much larger forest of gas and stars. The number is a reference, not a rule. It gives a sense of neighbourhood size. The scale shift remains calm. Heating events can vary on days. Gas flow can respond over thousands of years. The cavity can persist over millions of years. The host system evolves over billions of years. The small clearing is a long-lived feature compared with the short flicker of any single event. Another visual anchor keeps the rhythm. Along the cavity edge, a thin ring of denser gas appears, a faint arc. The arc is brighter where filaments feed it. The filaments arrive at angles, they shear into layers. The layers stack like soft ribbons. The ribbons show a gradient from dense to diffuse. The gradient marks mixing. The payoff arrives in the ring's function. The ring can become a reservoir. Gas that cannot fall inward collects there. Over time, the reservoir can trigger star formation at the edge rather than the centre. The black hole then changes the location of activity without being seen. Limits arrive softly and clearly. It is hard to attribute a cavity to a black hole alone. Stellar winds and other processes can also carve hollows. Turbulence can mimic clear regions. Projection effects can hide true geometry. Gas can be multi-phase with cold clumps inside hot plasma. Different phases emit differently. The limit is that observations often trace only one phase at a time. Models must infer the rest. Another limit is resolution. 10 light-years can be small at extragalactic distances. The cavity edge can blur into a smooth profile. A signal would be clearer with finer spatial resolution and multi-wavelength coverage, but coverage is limited. Another payoff resolves what still can be diagnostic. A cavity aligned with a central potential and accompanied by a consistent temperature rise toward the center can support the feedback interpretation. A ring that remains centered over time can suggest a gravitational anchor. A velocity pattern showing mild outflow or suppressed inflow near the center can reinforce the case. The evidence remains circumstantial. It can still be coherent. The section closes with a gentle transition. The next step moves from environmental influence to population clues across many systems. The view shifts from one cavity and ring to statistical trends that reveal whether intermediate mass black holes are common or rare. A single candidate can be debated, but a population trend can change the whole picture. Intermediate mass black holes become more credible when many weak hints align across many systems. In that region, the task is not to find one perfect signature. The task is to see whether several imperfect signatures repeat in the same direction. 3 ideas stay enough. There are scaling relations, there are selection effects, there is population inference. The first physical detail is a recurring shape in central profiles. Some systems show a slight central rise in velocity dispersion. Some show a smooth core that resists collapse. Some show faint, persistent nuclear emission. Each clue alone can be ambiguous. Together they can form a pattern. A visual anchor settles the scene. Many small galaxies and star clusters appear as faint smudges and soft spheres. Each has a center. Some centers have a tiny knot of light. Some have a slightly flattened core. Some have a dim haze that clings to the nucleus. The ensemble looks like a field of quiet embers. Most embers are faint. A few flicker a little. None dominates the darkness. The first payoff arrives in a simple idea. If intermediate mass black holes are common, their effects should recur. The recurrence can be tested statistically. This answers a small question. How can weak evidence become strong without a single definitive event? The answer is repetition across independent systems. Scaling relations enter gently. A scaling relation is a trend between 2 properties. It is not a physical law, it is an empirical pattern. In galaxies, central black hole mass can correlate with bulge properties. In smaller systems, the relation can be different. The presence of intermediate mass objects can appear as a continuation or a break. A break is itself a clue. It can suggest different formation paths. Another payoff arrives in the usefulness of a break. A break can separate seeds from giants. It can reveal where accretion dominates versus where mergers dominate. It can also reveal where feedback becomes important. The second concept enters with a short definition. A selection effect is a bias in what gets detected. It occurs when bright or loud sources are easier to find. It also occurs when certain distances or environments are overrepresented. This concept matters because intermediate mass black holes are difficult to see. Many will be missed. The observed sample can be skewed toward unusual cases. The third concept is population inference. It is drawing conclusions about an unseen population from a biased sample. It relies on models and corrections. It is not purely observational. It is an interplay. A physical detail ties the concepts to reality. Detection pipelines favor flares over steady dim emission. They favor strong gravitational wave chirps over quiet systems. They favor clusters with well-measured stellar motions. This creates a catalogue with sharp edges. It can overrepresent extreme candidates. It can underrepresent typical ones. Another visual anchor keeps the rhythm. Imagine a wide landscape at night with scattered fireflies. Only the brightest flashes are noticed at first. The quiet glows remain unseen. Over time, with repeated scanning, more are found. This is an analogy for selection. It stays gentle and unique here. It also contains a payoff. The absence of detections does not equal absence of objects. It can equal limited sensitivity. One number anchors the scale gently. A survey might examine about 10,000 star clusters across many galaxies. That is like counting 10,000 pebbles on a shore to infer the types of stones in the whole bay. The number is a reference for statistical power. It suggests that rare objects can still appear. It also suggests that non-detections can still be informative. The scale shift remains calm. An individual observation lasts hours or days. Survey programs span years. Cluster evolution spans billions of years. The sample is a thin slice of time, yet it can still reveal long-lived structures. Another payoff arrives in the role of upper limits. If many clusters show no central rise above a threshold that can constrain how many contain large central masses, constraints are part of knowledge. They narrow the possible fraction. They also guide where to look next. Upper limits are quiet facts. They reduce speculation. Limits arrive softly and clearly. Scaling relations can be misread when measurement errors are large. Stellar mass estimates can be uncertain. Velocity dispersions can be inflated by binaries. Nuclear emission can be contaminated by other sources. Gravitational wave masses can have degeneracies with spin and orientation. The limit is that each observable has confounders. Population inference must model those confounders. Different models can yield different inferred fractions. The results can depend on priors. They can also depend on how candidates are classified. A signal would be clearer with uniform data quality across the sample, but uniformity is rare. Another payoff resolves what improves confidence. Cross-validation across methods helps. If systems with dispersion rises also show faint nuclear emission, if gravitational wave events suggest a similar mass range, if dwarf galaxy nuclei show consistent core structures, then the independent lines begin to align. Alignment does not prove each case. It strengthens the collective picture. It can suggest that intermediate mass black holes are not isolated curiosities. They can be part of a broader population. Another visual anchor closes the section. The field of quiet embers becomes a map. Some embers cluster in dense regions, some sit in isolated dwarfs. The map shows gradients and gaps. The map is incomplete. It still guides the next step. The section ends with a gentle transition. The next step moves from population hints to the boundaries of current methods. The view shifts from what is suggested to what remains uncertain and to how future techniques could reduce ambiguity. A boundary in knowledge can feel like a boundary in space even when the space is calm and dark. Intermediate mass black holes remain uncertain because the signals that reveal them are small and easily confused. In that region, three ideas stay enough. There is resolution as the ability to separate fine structure. There is degeneracy as different causes producing similar signs. There is calibration as the need to anchor models with known cases. The first physical detail is the blurring of central gradients. A core that truly rises steeply can look flat when averaged over a broad beam. A tight nucleus can merge into surrounding light. A faint ring or knee in the profile can vanish. The inner boundary of influence becomes indistinct. A visual anchor settles the scene. A distant cluster appears as a soft orb. Its center glows like a candle behind thin paper. The candle has a brighter spot at the core. The paper smooths the spot into a gentle haze. Around the haze, the outer stars form a grainy halo. The halo is mottled. Some patches look denser only because of chance alignment. The first payoff arrives in a clean lesson. A missing feature in an image does not mean the feature is absent. It can mean the feature lies below resolution. This answers a small question. Why do some promising environments still show no decisive central signature? The answer can be that the relevant scale is too small. The influence region can be smaller than what can be separated. The second idea enters as degeneracy. It is described plainly. Many different mass distributions can produce similar light. A central black hole can raise velocities. A tight concentration of dark remnants can also raise velocities. Unresolved binaries can inflate measured dispersions. Tidal heating can broaden speeds as well. The same outward symptom can come from different inward causes. Another payoff arrives in the role of profile shapes. A genuine black hole influence can create a specific curvature in the dispersion profile. It can also create a characteristic change in the slope of the density profile. Yet a multi-mass cluster can mimic this curvature. A dwarf galaxy nucleus can hide multiple components. Without clean separation, the profile can be fitted in several ways. The first physical detail returns as a subtle knee in the gradient. The knee is the point where the slope changes. It is small. It can be smoothed away. The third idea enters as calibration. Calibration is anchoring models with cases that are understood. In this context, it means testing dynamical models on systems where the mass distribution is otherwise constrained. If models misestimate mass in known cases, they will misestimate in unknown cases. Another payoff arrives in the purpose of calibration. It reduces systematic error. It clarifies what a model can and cannot infer. It also clarifies the cost of assumption. The cost can be hidden. It can appear as confidence that is too narrow. The section keeps a gentle everyday analogy. It resembles reading a landscape through frosted glass. Hills and valleys remain visible. Small stones disappear. A distant lamp becomes a diffuse glow. The frosted glass stands for limited resolution and noise. The payoff is immediate. Broad structure can be inferred while fine structure remains uncertain. This does not invalidate inference. It sets boundaries on what can be claimed. One number anchors the scale gently. The influence region might be about 1 light-year across in some clusters. That is like a small room within a vast building of stars. If the room cannot be resolved, the building is still visible. The specific rim remains blurred. The scale shift remains calm. Orbits in the inner region can change on years. The cluster evolves over billions of years. Measurements occur over nights and seasons. The attempt to infer a billion-year story from short observations is a fragile bridge. Another visual anchor keeps the rhythm. A dispersion map is imagined without instruments. The cluster is divided into concentric rings. In each ring, the spread of stellar speeds is represented as thickness. Near the center, the ring thickness might increase slightly. Farther out, it might flatten. The increase is a faint bulge in the pattern. The bulge could be a black hole. It could also be a concentration of remnants. It could be measurement bias. The payoff arrives in the logic of multiple tests. If the bulge persists under different modeling assumptions, confidence grows. If it vanishes when binaries are accounted for, confidence falls. If tidal effects are modeled and the bulge remains, confidence rises again. Knowledge advances through robustness, not through one fit. Limits arrive softly and clearly. Gravitational wave detections face their own degeneracies. Mass estimates can trade off with spin. Distance and orientation can blur the true scale. Some events can lie near boundaries between categories. That can create apparent gaps or clusters. In electromagnetic signatures, faint nuclear emission can come from processes unrelated to a black hole. Dust can obscure. Gas phase can change. Intermittency can hide long-term behavior. The limit is that many channels are incomplete and noisy. A signal would be clearer with continuous monitoring and higher sensitivity, but monitoring is not continuous. Another payoff resolves how progress still happens. Combining channels can reduce ambiguity. A dynamical hint plus a gravitational wave hint in the same mass range strengthens the case. A consistent trend across many systems strengthens it further. Even null results shape the landscape by narrowing fractions. The section closes with a gentle transition. The next step moves from limits to perspective. The view shifts from what cannot yet be seen clearly to why the missing link matters for cosmic history. The tone remains steady and settles toward a softer, wider frame. A missing link matters most when it quietly changes the shape of a whole history. Intermediate mass black holes can act as long-lived waypoints that help explain how small systems and large systems share a common thread. In that region, 3 ideas stay enough. There is seeding as the start of a central mass. There is coevolution as mutual shaping between a core and its host. There is the fossil record as long-lived structure that preserves earlier conditions. A visual anchor settles the scene. A faint dwarf galaxy drifts through a larger halo. Around it, delicate stellar arcs curve like thin shells. The arcs are layered. The inner arc is sharper. The outer arc is softer and more diffuse. Between them, a gradient of starlight fades into the dark. The arcs look like quiet ripples frozen in place. The first payoff arrives in a simple link. Those shells can mark past encounters and past mass growth. A central black hole can influence how tightly stars remain bound. It can also influence how gas once settled. The shell pattern becomes a long memory. It suggests that even small central masses can leave a lasting imprint. Seeding enters gently as plain language. A seed is the starting mass that later growth builds upon. If the seed is too small, reaching large masses becomes harder within the available cosmic time. If the seed is larger, steady growth can be enough. This answers a small question: why the earliest massive black holes appear too soon in some models. A heavier seed shortens the required path. It also reduces the demand for perfectly efficient feeding. A physical detail anchors the idea. Near the dwarf's center, the stellar density profile shows a mild flattening. It is a core rather than a sharp cusp. The core has a boundary where the slope changes. The boundary is not crisp. It is a soft knee. The knee can reflect long-term heating by gravitational interactions. It can also reflect the presence of a central compact mass. Another payoff arrives in how coevolution stays quiet. A central mass deepens the potential. A deeper potential changes orbital families. Over time, orbits can become more mixed near the center. That mixing can smooth sharp features. It can also make the inner region more resistant to disruption. The host shapes the core by supplying mass. The core shapes the host by adjusting the inner structure. A gentle analogy frames the fossil record. It resembles layers in ancient ice. Each layer is thin. Each layer captures a moment of dust and chemistry. The whole stack becomes a calm archive. In the same way shells and cores can preserve past events. The payoff is immediate. Even when the original gas is gone, the stellar structure remains. Another visual anchor keeps the rhythm. The dwarf galaxy's shells extend outward. They become faint ribbons. The ribbons twist slightly along their length. Their brightness is uneven. The inner edge of each ribbon is sharper. The outer edge is more feathered. This edge contrast is a physical detail tied to phase mixing. It also hints at how long the structure has been evolving. The scale shift remains calm. The stars in a ribbon complete orbits on millions of years. The ribbon itself can persist for billions of years. A short-lived event can leave a long-lived trace. Another payoff arrives in why intermediate masses are special in this archive. A stellar mass black hole is too small to dominate large-scale structure. A supermassive black hole can dominate so strongly that it erases delicate traces through strong feedback. A middle mass object can sit between those extremes. It can influence a nucleus without overwhelming the larger system. It can also survive in environments where giant black holes do not form. This makes it a plausible common ingredient. One number anchors the perspective gently. A galaxy halo can span about 100,000 light years. That is like the difference between a single raindrop and a whole cloud layer spread across the sky. The number is large. It places the dwarf and its shells inside a much larger frame. The scale shift continues softly. The central region changes on shorter times. The halo changes on longer times. Both remain connected through gravity. Limits arrive softly and clearly. The fossil record is incomplete. Shells can fade and dissolve through mixing. Cores can be altered by later events. A central mass can be inferred from dynamics, yet dynamics can be confounded by unseen remnants. Gas histories are even harder to reconstruct. The early seeding stage occurs at great distance in time. Direct views of that stage are limited by faintness and by crowding in the center. A signal would be clearer if the inner motions could be resolved cleanly in many systems, but resolution and sensitivity remain finite. Another payoff resolves what still can be learned. Relative comparisons help. If dwarves with similar mass show different core shapes, a central mass difference can be one explanation. If shells appear more coherent in systems with stronger central binding, that can be another clue. Population trends across many dwarfs can turn uncertain cases into a coherent story. The missing link then becomes part of the logic of cosmic assembly. It connects early seeds to later giants. It also connects small hosts to large hosts through shared mechanisms. Another visual anchor returns to the center. The dwarf nucleus appears as a tiny bright knot within a smooth core. The knot is not a sharp point. It is a slight enhancement with a gentle gradient. Around it, the core light is calm and even. Farther out, the shells curve and fade. The whole system looks like a quiet diagram drawn in dim light. The payoff is in the harmony of scales. A small central influence can coexist with vast outer structure. It can shape the inner archive while leaving the outer memory intact. The section closes with a gentle transition. The next step moves from perspective to closure. The final section gathers the arc into a soft landing that rests on what is known and what remains open without tension. A quiet conclusion forms when scattered clues align into a single gentle scale. Intermediate mass black holes fit between stellar remnants and supermassive giants. They become a bridge that makes cosmic growth feel continuous. In that region, three ideas stay enough. There is continuity as a smooth range of masses, not separate islands. There is inheritance as earlier structure shaping later structure. There is humility as a clear boundary between signal and guess. A visual anchor settles first. A star cluster hangs in darkness like a soft lantern. Its outer edge is ragged. Its center is denser and smoother. The light near the middle rises, then eases into a shallow core. Inside the core, a subtle shadow of gravity shapes motion. The first payoff arrives in a simple anchor. A hidden mass does not need bright emission to matter. It needs only to bend paths and time. A black hole in the middle changes the speeds of nearby stars. It changes which orbits remain stable. It changes how close passages redistribute energy. The change is gentle in each encounter. Over long time, the change accumulates. Continuity enters as plain language. If black holes exist at many sizes, growth can move step by step. There is less need for rare leaps. There is more room for ordinary processes. A seed can grow through repeated small additions. Separate seeds can merge when hosts merge. The missing link becomes a set of stepping stones. Another payoff follows from the same idea. A galaxy does not need to start with a giant core. A giant core can be the end of many quieter histories. A small nucleus can carry an intermediate black hole for billions of years. Later, the nucleus can join a larger system. The intermediate mass then becomes a contribution to a larger center. In that region, inheritance becomes visible through structure. The second visual anchor appears. A dwarf galaxy drifts through a larger halo. Around it, faint shells curve like thin rings of mist. The inner ring has a sharper edge, the outer ring looks feathered. Between them, starlight fades along a smooth gradient. The shells are not new. They are long echoes of earlier tides. The payoff arrives in what those echoes suggest. A central mass can help a nucleus stay bound during disruption. It can also help preserve a compact core that survives longer. The shell pattern becomes a quiet archive. It hints at how small systems deliver dense centers to larger systems. A single number anchors the scale without strain. An intermediate mass black hole can be about 10,000 solar masses. That is roughly the mass of 10,000 suns. The number feels large. It remains small beside the giant centers of large galaxies. It sits in a middle range where influence is local and persistent. A physical detail ties the number to form. Near the center, a boundary of influence has a soft edge. Inside that edge, stellar speeds rise slightly. Outside it, the rise fades into the broader cluster motion. The transition is a gentle knee in the profile. The knee can be blurred by distance and crowding. It can also be mimicked by other hidden masses. Humility enters as a calm limit. A signal would be small in exactly the places where confusion is easy. Dense centers blend light into a smooth glow. Motions overlap along the same line of sight. Different mass layouts can fit the same observations. Single curve can accept more than one story. This limit is not failure. It is the shape of inference in a quiet universe. Another payoff follows from accepting the limit. Confidence grows when different lines of evidence agree. If central motion suggests extra mass, other properties can be checked for consistency. A stable core can support the same conclusion. A persistent shell pattern can support it too. A population trend across many systems can reduce the power of coincidence. The story becomes statistical rather than singular. The third visual anchor arrives with slower rhythm. A stream of stars arcs away from a disrupted cluster. The stream is thin at first, it broadens with time. Along the stream, brightness gathers into gentle clumps. The clumps are not deliberate. They arise from orbital phase and small perturbations. The stream has a spine and soft edges. The spine holds memory longer. The edges dissolve into the background. The payoff arrives in what streams teach. Gravity writes histories into shapes. A long thin stream means a long gentle pull. A wider stream means more mixing. A compact surviving nucleus means stronger binding at the centre. A hidden intermediate mass can contribute to that binding. It does not need to dominate. It needs only to persist. The scale shift remains calm. A close passage between two stars lasts hours. A star's orbit in a cluster lasts thousands of years. A cluster can evolve for billions of years. The same physics spans these times. Small deflections become large reorganizations when repeated long enough. Another payoff settles the arc. The missing link matters because it connects timescales. It offers a pathway from early seeds to late giants. It offers a pathway from small hosts to large hosts. It also offers a way to understand why some nuclei remain compact while others disperse. Continuity becomes a gentle promise. The universe may not jump as often as it seems. It may climb through many quiet steps. A final limit is stated softly. Some intermediate black holes may remain hidden for a long time. Some may leave only indirect traces. Some environments may never preserve clear signatures. Resolution will always be finite. Noise will always exist. Models will always carry assumptions. This boundary does not erase meaning. It clarifies how careful claims must be. The last visual anchor quiets everything. A dark centre sits inside a pale halo of stars. The halo fades outward into emptiness. The centre remains unseen, yet its presence is felt in smooth motion and balanced structure. Light behaves as a calm tracer. Orbits behave as slow sentences that repeat. The scene holds steady. The arc across scales closes without tension. The next moment can remain still with only gravity and time continuing their quiet work.